Well, we'll see if I can make it through today without coughing violently. We'll see. So I'll begin with a word of prayer here once I get settled. Dearly Father, we thank you for this day again. I thank you for these students, this class. Just pray that you just be glorified in what we do, and that we'd all understand a little bit more about your creation together today, Lord. In your name I pray, Lord Jesus. Amen. Do you guys have any questions before I get into my prepared remarks? Let's see here. Well, hopefully prepared. Yeah. Oh, yeah.
When are you going to release the questions for next week?
Like today? Yeah. I meant to last night. I just fell asleep. My old nemesis, sleeping, you know. Actually, I fell asleep, and then I woke up, and I was too tired to think, which was like counterproductive, you know. Like sometimes you take a nap and you wake up, and it's like, oh, okay, I'm good to go. But not the case for me yesterday. But yeah, I do need to tell you that. My encouragement to you in the meantime would be, oh, here, let me just pick out a couple. So whatever else happens today, you got a couple to chew on, right? I think I took the mission out. Well, it has to wait. I took my printout of it out, so I could look at it when I went home, and then here we are. So, all right. So today we're proving fundamental thermocalculus part 1 and 2. I will try to give, efficient proofs of these things. But we need to talk to start with. We need to talk about properties of the definite integral. So, just a reminder, the integral from a to b of f of x dx is defined to be the limit as n goes to infinity of the summation, let's say I equals 1 to n of f of x sub I star delta x, right? Where delta x is b minus a over n, and x sub I star is an element of the subinterval x sub I minus 1 to x sub I for I equals to 1 to all the way out to n, and x sub I itself is defined to be a plus I delta x. That is just your reminder. There's the definition of the so-called Riemann integral. It's defined to be the limit of the approximating sum, where the number of approximating rectangles goes to infinity. And we talked a little bit about what this means. We talked about area functions last time, right? So let me draw a couple pictures here. Let me plug in my computer so it behaves. So what do you think properties of the, can you guys tell me, what do you think some properties of this finite, of this definite integral would be? Like what if we had the definite integral of, well, let me not draw a picture. Good grief. Sorry, guys. So here are the properties. Let me write the properties first, then I'll tell you the picture if we want. Maybe you guys can tell me the picture. Come on, computer. Wake up. All right, so this is technically my proposition 6.2.23, which is on page 212 of your notes. Anyway, so here's part 1. If we have the integral from a to b of f of x plus g of x, Well, that's equal to the integral from a to b of f of x dx plus the integral from a to b of g of x dx. That's pretty easy to understand if you think about how do we get a graph? If we have f and we have g, we have f plus g. How do you make the graph? You just do what? You just add the values at each point wise, right? So like you can almost visualize this if you just kind of think about it. The other one, property number 2, is if I have the integral from a to b of a constant times f of x, well, that is equal to a constant times the integral of f of x dx, again from a to b. So you can pull a constant out. Again, this is fairly easy to visualize. Take for a specific instance, like c equals to 2. What happens if you take a graph and multiply it by 2? What does it do? It makes every y value twice as big, right? So if you think about the area, the x not having changed, the area would just be doubled, right, if the height is increased by a factor of 2 for all the rectangles. And this one, 3, is maybe the most geometrically obvious one. And here's how this goes. Integral from a to b of f of x dx is equal to the integral of a to c of f of x dx plus the integral from c to b of f of x dx. I'll draw a picture for this one. So what this property 3 is saying is if we've got, a and then c and then b, like so, right? And if you've got, your function, like this, let's say, whatever, then if we look at the area, so like this part, right, would be the integral from a to c f of x dx, right? And this part over here would be what? The integral from c to b of f of x dx. Yeah? And so if you have the area from a to c and then you add it to the area from c to b, what do you get? You get the area bounded all the way from a to b. So do I need to prove this, or do you guys just think it makes sense? It makes sense. That's good. Because it took me like 3 hours of a faculty meeting once to actually prove this, which is the thing you'll see in the notes if you look. I have a stupid proof of this, which is rather technical and annoying. But it's geometrically obvious, but actually a real pain to prove. And people with a deeper understanding of integration would say, you can't even prove that. That's like almost an axiom of the integral. All right, so there's that. And I do have proofs in the notes, which you can look at, which I'm not. But I think these are geometrically obvious, so we're going to go on. All right, so there are other properties of the definite integral involving properties involving inequality. So these are also important, all right? And so here's what those are. We have, sorry, I'm trying to give you guys, we're on 6.224. 6.224 actually, 6.2.24. So property number 1 is that if f of x is non-negative, f of x is greater than or equal to 0 for all x in a to b, then the integral from a to b of f of x dx is what? What can you say if the thing you're integrating is non-negative? What does that make the integral? Non-negative, right? You're adding up little areas. They're all positive or 0, so that's greater than or equal to 0. Number 2, we have this comparison. If you have f of x is greater than or equal to g of x for all, a less than or equal to x less than or equal to b. So this right here, just a point of, mathematical prose, I guess. You could either write this for all a less than or equal to x less than or equal to b like that, or like I did up here. This has the same meaning. Okay, those have the same meaning in terms of their, they're saying the same thing. And if that's the case, then what? Then the integral from a to b of f of x dx is greater than or equal to the integral from a to b of g of x dx. Right? Because of course the area that's under a larger function is larger than the area under a smaller function. Excuse me. The proof of these all stems from just applying like the squeeze theorem or the corresponding estimate theorems for limits to the definition. Right? So these things can be proved. And then 3, and we almost did this last time. Number 3, we sort of did last time in a sense, I think. But it's just kind of, again, somewhat obvious here. If your function is bounded, if you have little m less than or equal to big, little m less than or equal to f of x less than or equal to big M, all right, for a less than or equal to x less than or equal to b, then m times b minus a is less than or equal to the integral from a to b f of x dx is less than or equal to big M times b minus a. Okay? Let me draw a picture. Let me draw a picture of part 3 just to show you why that's a plausible theorem. So, if I am saying I've got a function, right? And just to make it interesting, I'm allow little m to be negative. Okay? I'll make little m negative just for the sake of throwing that idea in here. But I may regret that. So here's y equals little m. And then, you've got, let's say, y equals big M up here. Right? So for the sake of keeping my thinking not too cluttered, I'm going to make the function be non-negative, all right? So right, so let's, and I usually draw the bounds as if they're positive, but the bounds could be negative as well, like a and the b. But I put them here, so I'll put them here. So here's a, let's say, here's b over here, right? So we're looking, our context basically is from here to here, right? So what's the area, the signed area, if you will, under y equals little m? That's a negative one, right? Because I've drawn little m as if it was negative. So let me do some sketchy stuff here for a second. So here, this area right here, right? That is negative. And what's the value of it in terms of its magnitude? Its value is literally little m times b minus a, right? That's what this is equal to in terms of, it's a negative number because m is negative, b minus a is positive, like that, right? Then you could think about the area under the curve, right? This guy right here, what would this be? Not big M, no. What? We have a notation for this, right? This is the area function based at a, going all the way to b. The area bounded by y equals f of x from a to b. This is the definite integral. So this is less than or equal to, well, this is less than or equal to 0, right? For my picture, but anyway, less than or equal to integral from a to b of f of x dx. Now, you can imagine the little m being positive. That wouldn't change things, right? Like if little m is the, well, Well, little m has to be 0 because I made a value of the function to be 0. So anyway, little m could at most be 0 because it has to be smaller than the values of the function. Okay, anyway, so then going on here, you guys see what's happening. If we look at the area of the big rectangle, right? You know, it goes all the way from here to here. That's b minus a times big M, right? So we've got big M times b minus a, and that's all that 3 says. Okay? Does that make sense so far? Yeah. All right. So last time I tried to motivate for you, why the fundamental theorem of calculus part 1 is true, right? Should I draw that picture again, or do you guys remember it? Let's see here. So the picture we drew last time was something like, here's my my area function based at a. I've got my function, It goes out here to x. I'm putting t on this axis and y this way. So I can use x as a variable independent of that, general there. And then here, if we look at a little extra, so this is a of x, this area over here, and this right here would be delta a, a little bit more a. The extra bit of area that goes from going to x plus delta x, like that, right? But instead of using delta x for this argument, we're going to swap out delta x for like x plus h. All right? And so this is x plus h, let's say. The thing we found last time, right? All right, this is the delta a I'm trying to picture. So to be more specific, that is equal to a of x plus h, right, minus a of x. That's delta a, the change in the area function. Our goal at the moment is to prove FTC I. So let me state that formally. Theorem. This is the fundamental theorem of calculus part 1. We'd like to show that the derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. That's what we want to show here. All right. The statement of the theorem in the notes has got a little bit more language, and if you want the precise statement of the theorem, look at the notes, okay? I try to write a little bit less in class sometimes just to emphasize the main thing. This is the main thing. Now, if we use the notation, if we call this the area function, right? We use the big area function of x, right? What are we trying to show? AKA dA dx equals to what? F, right? So how do you calculate a derivative? So the proof is going to rest on us calculating the derivative of the area function. So let's walk through how to do that. So first of all, delta a, right, is the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt. How can we rewrite this right here? We can use property number 2, right? Oh, wait a minute, excuse me. Yeah, property number 3. Property number 3 from the start of class. right? Property number 3. See, because this right here, we can trade for integral from a to x, f of t dt, plus the integral from x to x plus h, I'm a dummy. Duh. X to x plus h of f of t dt. If I drew a picture, it'd become more obvious, but anyway, there it is. Minus the integral from a to x of f of t dt. I think at the end of it, I'm just reproducing what you would have already maybe written by intuition from the picture anyway, right? Which is like the difference of a of x plus h and a of x is literally just equal to the integral from x to x plus h of f of t dt, right? Okay? Now what else do we know? I guess I should tell you, we are making so I told you there's some more fine print to the function, to the theorem. Here's the fine print that I'm going to assume for today's proof. I'm going to assume that f is continuous. All right, we're going to assume that f is a continuous function at the values of interest here. So we'll assume f is continuous right. So we have f is continuous on the closed interval x to x plus h, right? Now, here we start to get into some issue of like notational clarity. Does h have to be positive? I mean, for my pictures, to be reasonable, h has to be positive, right? But when you actually calculate a derivative, do you just let the thing you're dividing by be a small positive quantity? No. The derivative is based on a double-sided limit, right? So the proper argumentation here has to allow for the make our positive case before we're like doing something wrong. What works in the positive case, the negative case would be opposite. We'll like almost the same argument, right? Picture it almost. One of the things is x a negative this on right fold small number to yet smaller interval between less than greater than. The interval 3 of x equal integral a to b of command back. Doesn't matter what you use as a letter. Is a notation for an explicit limit process how to input function tables taking the number of angles to be and width equals 0. All that. There is x and there's no x in the answer. And if it is number that represents the idea. So like there is nothing back to bed. Instead is fine. And it has to be there. X has separate but from G. All right. I could use here to use how to use exactly choice. All right. And it's positive, right? Via A, we have f of t. Let integral f to x plus h f t is equal to e. Right? And f is again where integral d by d is the nerve x plus term. Right? How do you calculate the limit? How do you calculate dx? Make dx equal what? The limit as h goes 0 of x plus h is of x over h. Now, we're going to get the right side of the limit from our limit as we want to do this positive. What is x plus say the work of the lower x is explained by property 3 of first operation. Like, this is for their function is equal to 0. 1 of h times 0 for x plus h. F of t here. Also, it's the limit. What do we think about the limit? You think about the limit. This is somewhat tough. And I think from an analyst perspective, it's a gap. But it's a gap where wow, limits. Right? What happens A is 0 right and just a line group? What happens? Step both C and D. Well, have both C and D is 0 right. They have to be there. So H is 0 right. This is from X. Just watch the output say X for C and D to X. Right. What can we say about this? Equal to that? In the right part of the we this plus and both of X there. The inequality f of n of d goes to x, limit goes to 0. Therefore, middle spread almost set to fx. That's f of fundamental calculus problem. Other f negative. Please don't do it. that picture will it. F2, we gave a correct proof. It's limited. That's true. But I haven't put F2 on you guys. We've so I'm gonna what is the what is it equal to? So I look at these. So your 0, your pi, your 2 pi. So the interval pi equal to. So the antiderivative goes up. This is FTC II. Fine. To the 3. I'll write because I get it. I should understand. Minus pi minus a minus cosine of 0. See? That what's going to because pi is 1. So cosine of 1 plus 2. Okay. Cosine of 2. Think 2 pi. Fine. Let's do it. My cosine of 2 pi. The cosine y pi is 2. Right? I see that is fine. So if that really the answer like this right here too. What the underneath the graph. So underneath the graph we get sine area of negative 2. Yeah. So and what the work out to? Minus 1 minus negative 2. Example 3. What interval derivative of sine x? We use previous two example, right? Let's look at it this way. Just by using previous examples, I go integral 0 pi